Okay, hi everyone. I'm Alyssa Brown and I'm a first year PhD student in Dr. Alex Hansen's lab. And today I'm going to be talking to you about magnetic components used in power electronics, specifically high frequency power electronics. So basically I want to give you the motivation behind all of power electronics essentially, which is something called power density, which is just the power processing capability of a circuit or converter over its entire volume. So if we look at a common power electronic circuit of a MacBook charger, you can see that it's composed of a lot of different things, but those circled in red are actually all of the magnetic components that are necessary for it to function. And you can see that in this case, it's taking up about half of the volume, and magnetic components in these circuits tend to take up either 1/3 to 1/2 of the entire volume of the circuit. So the goal for us then is to decrease the size of these components in order to increase power density. So the magnetic devices used in power electronics are fairly simple. They're inductors and transformers, and they're both derived from the same physics, that being Ampere's law, Faraday's law, and maybe some boundary conditions if you have a gap. They run on similar aspects, as I was saying. They have windings, and then they in turn have voltage to current ratios defined through that physics. And so really the main point of these devices is that for an inductor in power electronics, it's used to store and release energy in a circuit, while a transformer is used to transfer power from one side to the other. So here is an image of an inductor working in a power converter. Basically, the blue is showing how the energy is being stored and released with the switching of this MOSFET, changing the action of the circuit. So now I'm going to go into kind of the materials side of what we want in power electronics magnetics. And this is through BH curves. We typically use B in power electronics because that's what we care about. And so we typically want high saturation, high relative permeability, low coercivity, and low remnants. And we want high saturation in order to have enough headroom for the current flowing through the inductor or transformer to not saturate the core. We don't want to saturate cores because when the core becomes saturated, inductors actually act as shorts, and that's not really helpful for transferring power or for releasing energy. And we also want a high remnants so that most of the flux, high permeability, so most of the flux is contained within the core and not flying everywhere. And then low coercivity and low remnants because we don't like hysteresis at all, because hysteresis means loss. And power electronics people hate loss. So we ideally want this nice flat curve with a saturation and a permeability. So moving on to a bit of the history. I mean, in 1830, Faraday, Henry, and others found self-inductance, and really it hasn't changed since. The fundamentals are still the same, but what really has changed in developed power electronics is power semiconductors, which are a little bit different from CMOS. But so starting in the 50s, we had the first one released, and over time, they've advanced and really enabled higher switching frequencies for these converters to operate at. So for instance, today we use GaN and SiC transistors, which can go into the tens and hundreds of megahertz frequencies versus MOSFETs, which were only in hundreds of kilohertz usually. And then on the magnetic materials side, they also developed with the increase in switching frequency. So basically to be better at operating at higher frequencies. One example that I'm giving is ferrites, because those are commonly used in high frequency, discrete magnetic components, not integrated. And then in also 1993, the performance factor was defined, which is just a really important figure of merit for magnetic materials for power applications. And it basically just gives you the power processing capability of the material at a given frequency. So developments in this field are all about high frequency, as I was mentioning, because high frequency typically means miniaturization of these components. So you can see kind of on this graph over here that as frequency increased to a certain point, the component got smaller, but then because of some issues with the core, the size did increase because we had to make up for the loss and things like that, but it's still promising. And I mentioned ferrites earlier, and these are two of the most common ferrites used in higher frequency applications. Manganese zinc, which can be good up to like 1 megahertz usually, and particularly nickel zinc ferrites are very good for up to, or have been shown to have high performance factors in the tens of megahertz region. So the challenges which we're facing right now in power magnetics are losses, of course. And that's because copper loss which is the loss from the windings, goes with frequency, the square root of frequency, and core loss, which is from the magnetic material, goes with either frequency itself or frequency squared. So it's not great, but it's okay. We're working on it. And then so you can see in this graph this is a nickel zinc ferrite material, and you can see that with an increase in frequency, there is an increase in the core loss on the y-axis. So what have people turned to? They've turned to air cores, and they've just were like, I don't like core loss, throw it out. So they decided to have no core, and air cores typically dominate in the 5 to 50 megahertz region, which is like a common region right now. Like I said, they don't have any core loss. They also don't have any weight or cost from a core. And air cores typically do get better at higher frequencies due to their permeabilities and things like that. And then, so I have an example over here of a team that made some in-plane like PCB inductors, and then also 3D printed inductors. And you can see that they're still kind of large, but the main thing is that they weigh a lot less. And the reason they're still large in volume is that the lower permeability, which I mean, it's air, so means that there's a low B field. And so you actually need more volume to contain enough flux for correct operation. And so, yeah, that's not necessarily great. And then there's also EMI issues, which basically just means that like stray flux leaks out of here, and that is not very good for like switching components. It can affect those. And then also they usually require more turns, which means higher copper loss. And so, but still people use them, like I was saying, in the 5 to 50 megahertz region. But this paper shows that they actually did some calculations and found some frequency boundaries for which core materials would actually work better than their air core counterparts. So anything like past these dotted lines would actually be better with a core. And so you can see that like into the 10s and 20s and 30s of megahertz, some cores would still operate better than air cores. And so like core materials still stand a chance there. And so what are the barriers to improvement in these magnetic materials? Basically, there's limited information on the power capabilities of a lot of like released materials, such as those used for RF applications. And that just means that the materials that these companies release are tested like at small signal. So they give a lot of small signal information, but we actually need like high flux density information because we care about it processing power, not really filtering. And then, well, it filters, but still. And then there's also, we have, like I mentioned before, we have like the constraints on BSAT and permeability, which typically limit our material choice. So how do we proceed? Well, this paper recommends that maybe we just like reassess some of the constraints on saturation and permeability. Basically, it's saying like at higher frequencies, we aren't necessarily as limited through from saturation as like people usually think we are in like the lower frequency domain. That's a big problem, but in high frequency, it's not necessarily an issue. And that's shown theoretically through this graph. And then similarly for permeability at higher frequencies, you don't actually need like the 1,000 permeability, which most companies like look for. And so it graphs the critical permeability that you need for a good inductor. And then you can see that it can be as low as like 10 for high frequency applications. And so maybe if we release some constraints on these, we can look at other materials and actually find something that might work for us in the high frequency domain. And that is all. Thank you.